Okay, the last thing we're going to talk about today is the Nernst equation, which is going to relate this electromotive force, this voltage potential, to an equilibrium constant. Okay? So we already know that delta G naught R is equal to negative RT log of K, the equilibrium constant. And we've seen from the last couple of chapters that K is a multiplication over all of the species in the reaction, and then an activity coefficient and a concentration. Or maybe K is a multiplication of a different kind of activity coefficient times a molality, depending on which theory we're applying. And whether or not we use concentration or molality, it's going to result in a different K, by the way. And also a different delta G R naught, depending on whether you're using the standard state molality or the standard state concentrations. So now over here into this equation, we're going to plug in what we saw on a previous slide, that this delta GR is equal to negative, that's supposed to be F, negative NF electromotive force in the standard state. By the way, this N is the number of moles of electrons transferred in the reaction. Okay, so just putting that right in there, what we get is that negative Fe naught is equal to negative RT log K. And then we just algebraically rearrange this a little bit, and we get that E naught equals RT over NF log K. So remember that K is in reference to a system at equilibrium. Now, with regards to batteries, if the battery is at equilibrium, then it's dead. It's a dead battery. And unfortunately, that's not all that useful to us. We would rather do calculations regarding systems that involve a live battery. So therefore, it's going to have to be out of equilibrium somewhat. And then as the reaction proceeds, it's going to approach equilibrium and the battery is going to go dead. So out of equilibrium, we can have a live battery. So now we can no longer use K. We have to use a non-equilibrium set of concentrations, which is going to make the variable Q instead of K, but it's really all of the same quantities, it's just out of equilibrium. And this K is called the reaction quotient. So again, all these same equations up here apply to big Q. We're just going to have a set of concentrations that are out of equilibrium. Then in that case, our equation will change slightly, and we'll have E, the electromotive force that the battery is imposing, is going to equal E naught minus RT over NF, and then this reaction quotient gets put in there like that. And this E right here represents the voltage induced by the electrochemical cell. And this is called the Nernst equation, and we're going to use it a lot for the remainder of the chapter.